Okay. Okay, so last unit, we talked about acids and esters. This unit, we're going to talk about acids and amines. And they're going to be very similar to an ester. Because there's always going to be two parts to amides, like proteins, for example. The bond that binds amino acids together to form a protein is called an amide bond or a peptide bond. You're in a biology class. Okay, amines are similar to alcohols in terms of primary, secondary, tertiary. There's even a quaternary one, which is a salt. And like alcohols, it depends on how many hydrogens are there. Now, if we look at nitrogen, that's what nitrogen looks like. So it's got three singletons. That means three bonds. So for example, ammonia. Speaking of ammonia, ammonia water makes a really good pesticide. It's totally non-toxic and kills pretty well. Like I have cockroach challenges in my house. My whole apartment complex has got cockroach challenges. Mine are at a minimum. I rarely see a cockroach because I have my spray bottle of ammonia water. Flies that go flying by, you have to wait for they land before you can smack them. Not with my spray, you just go and they fall to the ground. Ants, and it's cheap. It's like 20 cents a bottle. You buy the concentrate for $3, Parsons brand. Go to the cleaning section of like Rayleigh's or whatever, $3.20. You put about this much in the spray bottle, the rest is water. Cool thing about it is ammonia is gas. So you can spray on your window, for example, you see it fly in the window, go, and you'll see all the wet stuff from the spray. Within a couple hours, it's totally gone. Because especially in the summer when the glass is warm, because the water evaporates and the ammonia gas evaporates. There's nothing left. Totally safe for pets. I have 3 dogs, so important for me. It really works well. I discovered that about, I don't know, 10 years ago or so. And I like to share it with my class because it's cheap. When you go buy a spray, a bug spray, it's like $5, $6. It's crazy expensive. And it's not very good for you or your pets. This stuff, good stuff. Okay, so because nitrogen has 3 singletons, it can have 3 bonds. Now there's a special case for oxygen and nitrogen. Oxygen has got 2 pairs of non-bonding electrons. Nitrogen has 1 pair of non-bonding electrons. So if you've got something that has no electrons, for example, that hydrogen has 1 electron, H plus has no electrons. So it wants to bond and become more stable. So what happens is it bonds to the pair on the nitrogen. So what you end up with is this. It's got an overall positive charge. So that is the quaternary form. Oxygen does the same thing with hydrogen plus. It forms a hydronium ion. So it's H3 plus, same idea. And that bond is called a coordinate covalent bond. That's the only time that pair of electrons bonds is in a coordinate covalent bond. It's something that has no electrons, like hydrogen plus. Now, acids, that's the definition of an acid. Does it dissociate an H plus? So if it's an acidic environment, you always have that coordinate covalent bond happening because it bonds to water. Okay. So that means we have quaternary versions as well. So we have primary, secondary, tertiary, quaternary. Okay, there's two ways to name an amine, IUPAC and common name. Now, most people, all they do is, remember when we were naming ethers? There's the IUPAC way, and then we have we name each side of the ether. It could be a methyl, ethyl ether, or whatever. Same with amines. Now, amines have got three parts. So name the non-hydrogen part. So in this case, we're looking at methyl. So it's methylamine. It still has two hydrogens though, because nitrogen has to have three bonds. Dimethylamine. Ethyl methylamine. So it's very straightforward. Now, on your packets, Dry Lab 2, the last page, they list functional groups. Amines are towards the bottom, that functional group, meaning that any functional group above that takes precedence in naming over the ones in the bottom. Well, if amino group is on the bottom, that means most things take precedence over the amine group. So in this case, we've got an alcohol and an amine. So that means this is going to be named as an alcohol as opposed to an amine. The amine then is going to be a branch. So the branch is on carbon 1, 2, 3, 4. That's going to be 4 amino. We have a bromo branch on carbon number 2, so it's going to be 2 bromo. And then the OH group is on carbon number 1. Now, if it's just an amine, an NH2, then you name it as a branch. So this would be the main chemical, propane. And you have a branch on carbon number 2, so it's 2 amino propane. Now, the last time I did this presentation, I was being evaluated by Dr. Huang, and he teaches organic, and that's his specialty when he was in graduate school. So he knows naming IUPAC really well. So I asked him, I said, if we name this, instead of a alcohol, what if we name this as an amine with an alcohol as a branch? In other words, so it's going to be so it's going to have a butane backbone. With three functional groups actually. So we're going to have a 1 hydroxyl, 2 bromo, and 4 amino, butane. I said, would that work as an IUPAC name? He said, no, but everyone uses it that way. It's kind of interesting response. Okay, anyway. The bottom line is the amino group is at the bottom of this list of functional groups. So if it's a mix of amino and something else, it's not going to be an amino base. It's going to be whatever the other one is. There's a hydroxyl group, it could be an alcohol, etc. Okay. Now the thing about the one tricky thing about nitrogens is if there's a group on the nitrogen, you've got to name that group. Okay, so let's take this one as an example. So we've got a 1, 2, 3, 4. So it's going to be a butane base. And the branch is going to be on carbon number 2. So it's going to be two butamine, except we've got a methyl group on that nitrogen. So to name the methyl group on the nitrogen, we're going to say uppercase N italicized methyl. As soon as we specify the N, that means there's something coming off the nitrogen. Now in these, we've got hydrogens. Hydrogens, you don't have to worry about hydrogens, only if it's non-hydrogen. Usually it's going to be a methyl or an ethyl group, at least in this class. Like, let's look at this one here. All right, so this is going to be a 1, 2, 3, 4, 5. That's going to be a pentaamine, carbon number 2, and it's got some methyl groups coming off the nitrogen. So we're going to go N dimethyl to pentaamine. And we're going to find when we have an amide, we've got to do the same thing. Now we can have like alcohols, we can have aromatic alcohols, phenol, can also have aromatic amines. Now, the base unit for an aromatic amine is going to be aniline. Just like with an alcohol, it's called phenol, this is called aniline. Aniline is not nice stuff. I have runny nose. Sorry about that. Okay. All right, so let's look at this here. Okay, so we've got an aniline here, but the aniline has got all kinds of stuff hanging off of it. Okay, for one thing, we've got an ethyl branch. And we have an amino group that makes it aniline. And we have a methyl hanging off of the nitrogen. So carbon number 2 has got an ethyl group. So we're going to go 2-ethyl. And because the amino group on the aniline has got a methyl group there, we're going to say N-methyl aniline. By the way, I could not put together in time a unit 3 dry labs. I have a unit 4 dry labs that I'm going to put there, just basically practice worksheets. I need to see if that's there yet. Anyway, there's an assignment that says unit 4 worksheets or dry labs. Okay. So that nitrogen, the N here stands for stuff's coming off of the nitrogen, except for hydrogen. Hydrogen doesn't count. So anything but hydrogen. Okay, so intermolecular forces. Primary, secondary amines can form hydrogen bonds, but they're not as strong as alcohol hydrogen bonds. Now, when you look at the carbonyl group, the nitrogen is partially more negative than the hydrogen. That's where the hydrogen bonding comes in. Hydrogen bonding is with oxygen, nitrogen, fluorine. And we don't talk about fluorine because fluorine is not in our bodies. But nitrogen and oxygen are very much in our bodies. So, but the bottom line is hydrogen bonding takes place. That means it's got a strong intermolecular force, okay? So that comes into play, boiling point, melting point, and surface tension. Now, tertiary does not have hydrogen bonding. Primary, secondary has hydrogen bonding. Now, things change rapidly. We start talking about, so this would be primary, 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 secondary, tertiary. So tertiary amines have very little intermolecular forces. LDF, obviously, because everything has LDF, but not necessarily hydrogen bonding or even dipole-dipole. So because water is very polar, amines are very polar, except for tertiary or quaternary amines. They're usually soluble in water, as long as the number of carbons is 7 or less. 7's the magic number on every one of these. Acids, alcohols, amines. So in other words, the London dispersion forces take over if it's 7 or more. Okay, because nitrogen has 3 bonds, you get a lot of steric hindrance on getting to this pair of electrons here, depending on how big those R groups are. So the primary amine is stronger hydrogen bonding than the secondary, which is stronger than the tertiary. Nitrogen compounds, like sulfur compounds, are very aromatic. Number two, they're very odoriferous or stinky. There are two chemicals that, when something rots, these two amines are given off, putrescine and cadaverine. And this is where the word putrid comes from, and cadaver. But as you know, anything smells like if you kill a mouse in your house with a trap and forget about it, something starts to stink after a while, you're smelling cadaverine and putrescine. Very strong. Okay. Anything with nitrogen in it acts like a base. Okay. That means all these amines and everything, including ammonia, act like a base. Meaning that what happens is the nitrogen grabs hold of a hydrogen in the water. So what happens is this nitrogen grabs one of these and leaves an OH left. So if we're talking about ammonia water, this is what it looks like. The name of that is ammonium hydroxide. Ammonia water. Because the coordinate covalent bond with the hydrogen on the water creates, because this bond doesn't need electrons because the nitrogen is supplying it. So it doesn't take any electrons with that hydrogen. It leaves them on the water. That's why we end up with a negative charge here on the water. Now this applies to most all nitrogen compounds. They're all basically on the alkaline side because they steal the hydrogen atom from water, leaving you with the OH. So, and remember with the acids and different pHs, bases also have ionic character in different pHs. In fact, the easiest way to remember it, it's the exact opposite of an acid. See, okay, so let's look at acids, bases. Okay, so pH less than 7 is acid. pH greater than 7 is alkaline or basic. Okay, so let's organize this differently. Okay, so that's acetic acid. This is ammonia. Okay, so let's throw in acidic conditions. That means there are these guys running around. So what happens is this goes over to the pair. pair on the nitrogen. So it becomes NH4 plus. That's in an acidic environment. With an acid in an acidic environment, there's no reaction. Okay, so let's look at pH greater than 7 in an alkaline environment. That means there's going to be OHs around. So in an acidic environment, nothing happens to the acid. In a basic or alkaline environment, what happens is the proton comes off. So you're left with that. Let's, and in a basic environment, what you end up with is the OH grabs the H off the nitrogen, and you end up with that. This will be on test 4. Guaranteed. Okay, so bottom line is this is ionic, non-ionic. This is ionic, non-ionic. So we can manipulate the solubility of a compound by changing the pH. If it's an amine or an acid. If we make it ionic, it'll dissolve in water. If we make it ionic in a basic environment, it'll dissolve in water. Now, this will come into play in the next subunit on proteins. We're going to have something called an isoelectric point. And we're going to study that in detail. Just for right now, an isoelectric point is the pH at which protein will become net zero ionic charge. In water, that means that protein solidified, also known as chi. So, for example, meat has an isoelectric point of 4. That means at pH 4, that protein is going to be non-ionic. As the pH goes away from 4, that protein becomes more and more ionic. Hence, the side chains on that protein, amino acids, start to repel each other and allows water to come into that protein. Also makes it tender, more tender. So I'm developing a lab to be done at home or fall. Well, basically what I'm doing is how to tenderize meat when you're cooking. Real factual stuff here. A lot of Asians say to add baking soda to your marinade on your meat. Problem is, if you don't wash off the baking soda, alkaline stuff is very bitter. So you end up with this bitter marinade. You don't want bitter marinade. So what you do is you treat your meat first with baking soda, which raises the pH away from pH isoelectric point 4. Proteins spread open, water comes in, it's more tender. Then you wash it off. Then add your marinade afterwards. You can do this with chicken, shrimp, pork, and beef. All works the same. So the lab at home is going to be basically going to be buying inexpensive protein, like chicken breasts on sale, and some kind of pork. Probably pork chop. And they're treated with different pHs. And then you're going to taste it each time. And it's a very sound, very old technique from Asian cooking. been around for hundreds, if not thousands of years. The Westerners don't seem to grasp the idea of spirit flow. Unless you teach chemistry, even chemists. I was talking to a colleague up on the third floor one time about 3 years ago, and I was developing this lab, and she didn't know where I slept. She was not an organic chemist or a biochemist, though. And she said, "Oh, I remember, but I don't remember what it was." That was a long time ago. But anyway, it's very cheap. Dude, baking sodas help people. So it's a really easy technique. And you do it for like half an hour. All it takes. You treat it first with baking soda, wash it off, and throw your marinade in there. Now you can also velvet it with cornstarch after you wash off baking soda. Works really well. You get that nice mouthfeel of the meat, with the chicken or whatever, and it's tender. You slice it nice and thinly. Works really well. But I got part-time instructors do not make up labs. Except me. Made a few labs before I did. Sierra won't let me do it, but that city allows me to do it. So, and the part on the aspirin that we skipped, that was what I invented. Acid equivalent. But so anyway, if anyone would like to try this at home, let me know how it works. We'll have some. I'll ask you a bunch of little questions about, what pHs did you try? So you'll be taking home some pH paper. That's the pH. The pH we're working at. So really, really a fun, easy technique. Okay. So I'm going to talk about this in a lot more detail when we get to Wednesday. Okay. There's a lab or a reaction called a neutralization reaction. That is acid plus base yields water plus salt. And the salt is a combination of the cation and the anion. So basically, think of water like that. Okay, so in the case of amines, we can have an amine, which is the base, plus the organic acid. So ammonium and whatever the acid 8 is. So if it's acetic acid, it'd be ammonium acetate or propionate. So acid base, so we take unit 3 acids, unit 4 amines, bring those together and we form, here's the salt. And water. Now sometimes the H from the acid is a coordinate covalent bond with the nitrogen. So there's no water produced. It's all internal. But these two stick together. Very, very polar also. Now, naming amino salts is the words get really big. So, let me clear some of this up. Okay, so a salt, the quaternary nitrogen compounds have two parts. Just like when we named some of the salts with acids. Okay, there's positive part and negative part. And so it's two separate words. Okay, in this case here, the first one, we've got that's one of them. That's the other one. So we name the ions separately. Okay, Br minus, that's an easy one, that's bromide. Now let's look at this. We have an ethyl group, two methyl groups. So it's going to be ethyl dimethyl ammonium bromide. Two parts, the anion, cation. Now the positive one is always named first. It's like it's always good to be a positive person. Same with chemistry. Positives always go first before the negatives. So here we've got three ethyl groups. So it's going to be triethyl, and then this here is the ammonium. And then that's acetate. Kind of big names, it's kind of awkward. Now, one thing when you're a pharmacist synthesizing new drugs, our body is made up of mostly water, like 97% water. So any drugs that are not polar don't move around very much. We're talking about motility of the drug. Motility is how easily we move around. Highly motile drug means it's very polar, dissolved easily in water. When I was a little guy, I had horrendously bad asthma. I was out of school literally half the time. And I can still read. I'm able to read all. I'm always up, barely breathe and sleep. Well, on top of that, my parents wanted me to get into band. So the band director decided they needed a sousaphone player. Who knows what a sousaphone is? A big horn requires lots of breath. I had asthma. Duh. Sorry, parents, that was not a good decision. So the treatment in the 50s for asthma was vitamin B12 shot in the butt. That was it. No antihistamine, none of that stuff was around in those days. So once a week, my dad would take me down and get a shot of vitamin B12. Early development of vitamin B12 were not very poor. So that thing sat in my butt for like an hour. I could not walk. So my dad would carry me down to the dime store and buy me a little peep. I still remember it to this day. It made me feel better. I'm getting all teary-eyed here now. But it was a motility issue and it had to do with the polarity of that molecule. So the pharmacist's job is to make sure that thing is polar so it can be picked up by the gloves. Now your problem comes in on fats. Your body does the same thing with fats. Fats are nonpolar. So one way to make them polar is to saponify them. So your body saponifies fats. The acid salt, very, very polar. Now it's soluble in blood, so you can move that fat around your body, and then it reforms again, triglyceride. Very clever, our body. So, as a take-home problem, quite a long time ago, I gave vitamin B12, the old version, the non-polar one. I said, make this polar. And they had to look at all the functional groups coming off that vitamin B12 and do reactions to make them polar. That was their take-home problem. So, for example, this is morphine. Morphine is not available as morphine, it's available as morphine sulfate. Ionic. Dissolves in your blood. Also very cheap. That's a problem with these. Don't lean on something that moves. That's a problem with a lot of these drugs. And one of their ECMA, some from opium. They did to modify that morphine into heroin, or black tar heroin. One reaction. Lots of impurities. That's why they call it black tar heroin. It's horrible for you. They get horrible drugs. Who's heard of crocodile? Bad stuff. Look at pictures of crocodile injection sites. Usually you can see the bone because it heats up the flesh around the injection. Their highs are extremely high, but they're very short-lived. The deal is you constantly get a new injection. It was invented in Russia quite a few years ago. But anyway, crocodile. Horrible stuff. Anyway, the other one, it was Sweden. Methamphetamine. It was invented by the Nazis in World War II. They gave their soldiers speed so they could walk a lot. And the formula for making speed in the field was developed by the Nazis. So it's very simple, very dangerous. They can make their own speed, their own method in the field. That's why in Breaking Bad, Walter modified that recipe because it was one explosive and gave ordeal. But you need that gluten. And by the way, that's based on a true story. Walter White exists. It's in Alabama. I have a video on it was interesting. Yeah, he was interviewed and everything. And of course, Breaking Bad, I have watched the series because I have an OT. And yes, it's fascinating. There's also all the chemistries available too that Walter White theoretically used. But the formula that everyone uses in the field, in crack houses, meth houses, is developed by the Nazis during World War II. And uses red phosphorus, it explodes a lot. It's really awful. And your hands get all dark from the iodine. But okay, anyway, sorry about the aside. But basically, drugs have got to be motile. They've got to be ionic to be able to move around in the blood. Now you can modify, like we talked about earlier over here, in an acidic and alkaline environment. That's what we talked about 3 slides ago. Now, when you're talking about quaternary salts, however, they exist as a cation, no exceptions. They're all cations. And you've got, always have 4 parts. None of them are H's. They're non-H parts. So you've got, this is the one part, and this is the other part, just like we talked about earlier on naming. And we've talked about choline before. That is a quaternary salt. So we've got 1, 2, 3, 4 non-hydrogens attached to that nitrogen. So that's why it's charged. This is a similar one, acetylcholine. Now, there's a lot of nitrogen compounds in pharmaceutical, household products, drugs, agriculture, a lot of pesticides have nitrogen compounds in them. I talked about the cholinesterase inhibitor of organic phosphate pesticides. It's got nitrogen in it as well. Now, now we're going to talk about amines. Amines are like esters. So you've got an acid group, and we've got a amino group. When we talk about amino acids, that amide is called a peptide bond. The same thing though, it's an amide. Okay, remember from Unit 3, there are 3 ways to make an ester. Okay, we've got the acid plus alcohol. We've got the acid chloride plus alcohol. So let me back up a second here. To make an ester, the poorest way to make an ester is with alcohol plus an acid. Okay, amines are the same thing. You make it with an amine to make an amide. The problem is the slowness of the alcohol is even slower with the amino group. It's so slow it doesn't exist. So this reaction to get to this here can't be done. So to make an amide, there's only 2 ways. You use the acid alcohol and the acid chloride or the anhydride. So let's take some examples here. So 3 ways to make an ester, 3 cross off 1 ways to make an amide. Acid chloride with amides have the highest yield for the same reason they make the highest yield esters. Acid chlorides are very unstable and they want to react to become more stable. That's why they have a poor shelf life too. And because of that, they're very expensive. This is the preferred way on both of them. The anhydride, just like we use the acetic anhydride when we made our aspirin. Good shelf life, reasonable yield. And no one uses the acid and alcohol to make an ester. And you can't make an amide with the alcohol excuse me, with the amine group and acid at all. It's just horrendously slow. Okay, so let's come up with something here. Let's make that. Okay, so we have this would be the acid part. This is going to be the amino part. So we're going to have a primary and secondary backbone again. Primary backbone is always the acid side. That's going to be the secondary backbone. Okay, so this is a 3-carbon acid. So we're going to start with propanoic acid plus ammonia. Let's name this two here. So we name the amino part first, and there's no groups other than hydrogen coming off that nitrogen. So this is going to be we name the amino part first. So it's going to be amino propa na amino. So okay, so we take propionic acid and ammonia. So this is ammonia. Gives us our amino propanon amide. Easy for me to say. Okay, so that's one trial. Okay, forest yield. Let's do it again with the anhydride. So the anhydride is going to have so this is di dipropyl anhydride plus ammonia gives us this guy. And then lastly, the acid chloride. So that's going to look like this. This is going to be So that's the three ways to make the amide, but this way it's too slow to even count. Now, what that means the propionic acid is more stable than the amide. Remember, things go from unstable to stable, not the other way around. If it was the other way around, we'd have to put a ton of energy into that to get us over the activation energy of that reactant. Okay? So let's do another one. Let's make that. Okay? And we know it's an amide, means it's an acidic part, amino part. So the acidic part is this guy here. So we have a primary backbone and a secondary backbone. So we named the amino group first. So that's going to be a N-N dimethyl. Amino. Then we name the acid part. So it's going to be a 3-carbon acid again. So it's going to be okay. So to make that 3 ways, I'm going to mention even the way that doesn't work. We start with the acid, which is going to be propionic acid. Plus the amine, which is going to be that, gives us this guy up here. So this is so that's NN dimethylamine. Okay. And let's do the second one, the anhydride. So dipropyl anhydride plus the NN dimethylamine. And then lastly, we're going to have the acid chloride. 3 ways. Okay. I'm going to end this here. So that we can start our lab early and go home, eat the rain. I'll pick up on one of them, so I'm almost done, so we pick up from there on the. Okay, so I want you to don't freak out on this. Think of it just like unit 3. We have esters, we have amines, very similar. Maybe a little trickier on the amino groups, but basically the chemistry is very, very similar. So, right? Yeah,
Can I run over like a poster that was doing? Awesome.
yeah, okay, poster and essay. You know, tell them what essay, know what it is. Think of a poster as a multimedia part of your essay. So put no diagram, no address. Look it up. And then all the diagrams going through. Get a 3-panel poster and stand up by themselves. If black's available, get black. And everything really pops with black, looks much better. And you can go through. You go to Canvas, Files. One of the folders is projects, and these are a whole bunch of examples. The projects are extremely diverse. I need to see some chemistry between the chemistry class. Like if you're doing a disease, for example, do one when you use chemistry. That was a challenge for Chris on her, the horse fell on her. Because she had lots of chemistry, so she ended up with synapse chemistry. And calcium ion, one parts of synapse. That was her chemistry. This office of chemistry. And I'm very lucid, I want you to be interested. If you're totally not interested in your project, just go for the examples and choose one. Okay? But I'd like you to do something with this. It could be hair stuff, makeup stuff, something going on in your family you want to study more. One person did it on the biochemistry of dying. What happens to all your tissue and all that stuff? When did rigor mortis set in and then it goes away? Chemistry things. One person did it on guitar strings. Why does one corrode and one doesn't? And that wasn't in a biochemistry class. I do it for my M300 class as well. I'm teaching 3 or 5 over the summer. I'll do it for them as well. But then it's going to be extra credit. No, actually, 3 or 5 requires 300. So does that help? Yes.
I have a favorite animal and I have a venomous, it's a loris, like a primate. It has a venomous elbow and I'm biological effects of when it bites to its eyes. So, I don't know that, would that be okay?
Yeah.
Okay.
What person's doing on, she wants to go into toxicology? So she had, embroidered on the back of the lunch coat. The plant that has the most, potent, alkaloid in it, in terms of death. And then she did the embroidery of the chemical itself. In the back of it, really kind of cool. Another one, she paid her sister to embroider on like. Maybe it's credit for it. So anyway, so your lab coats, be creative. Doesn't have to be tie-dyed, it has to be embroidered, just whatever you like, just decorate. You can use it in other products, so except for micro. Micro is real picky about which you can use in the lab. Other than micro. Have it. Okay? Are you okay with that explanation? Okay. Everyone always asks me, what's the rubric? There's a rubric. Anyway, look for. Or not. Okay, any more questions? All right.